In the early 20th century, physicists stumbled upon a strange and counterintuitive realm, the quantum world. This realm, governing the behavior of atoms and subatomic particles, defied the laws of classical physics established by giants like Newton and Galileo. Quantum physics, also known as quantum mechanics, emerged to explain these peculiar phenomena and revolutionized our understanding of the universe. Imagine a world where objects can be in multiple places at once, or where information can travel instantaneously across vast distances. This is the bizarre and fascinating world revealed by quantum physics. It challenges our everyday intuition and forces us to rethink our fundamental assumptions about reality. Quantum physics is not merely an esoteric theory confined to the minds of physicists. It has profound implications for our understanding of the universe and has led to groundbreaking technological advancements. From lasers and transistors to medical imaging and quantum computing, quantum physics is transforming our world in profound ways. To grasp the essence of quantum physics, we must venture into the realm of the ultra-small, where the familiar laws of classical physics break down. In the macroscopic world, we can describe the motion of objects with precision. We can determine their position and velocity at any given time. However, in the quantum world, things are not so straightforward. Atoms and subatomic particles, the building blocks of matter, do not behave like miniature billiard balls. They exhibit wave-like properties spreading out like ripples on a pond. They exist in a haze of probability, their exact location and momentum uncertain. In the quantum world, energy comes in discrete packets called quanta, like tiny bundles of energy. This is analogous to a staircase, where you can only step on specific steps, not in between. This quantization of energy has profound implications for the behavior of atoms and the interaction of light and matter. One of the most mind-boggling concepts in quantum physics is wave-particle duality. This principle states that light and matter exhibit both wave-like and particle-like properties. This duality is not an either-or situation, but rather a both-and reality. For centuries, scientists debated the nature of light. Isaac Newton proposed that light was composed of tiny particles called corpuscles, while Christian Huygens argued that light was a wave. In the early 20th century, experiments showed that light could behave as both a wave and a particle, defying classical categorization. The famous double-slit experiment demonstrated this duality in a striking way. When light is shown through two narrow slits, it creates an interference pattern on a screen behind the slits, just as waves do. However, when individual particles of light, called photons, are sent through the slits one at a time, they still create an interference pattern, suggesting that each photon interferes with itself. Another peculiar feature of the quantum world is superposition. In classical physics, an object can only be in one state at a time. For example, a coin can be either heads or tails. However, in the quantum world, a particle can exist in multiple states simultaneously until it is measured. Imagine a quantum coin that can be both heads and tails at the same time. This may seem nonsensical, but it is a consequence of the probabilistic nature of quantum mechanics. The coin exists in a superposition of states, with a certain probability of being heads and a certain probability of being tails. When we measure the state of the quantum coin, we force it to collapse into one definite state. The act of observation disrupts the superposition and determines the outcome. This is analogous to opening a box containing Schrödinger's cat, a thought experiment that illustrates the strangeness of superposition. Section 5. The uncertainty principle. Embracing the unknown. One of the most profound implications of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg. This principle states that there are fundamental limits to the precision with which we can simultaneously know certain pairs of physical properties of a particle. For example, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not due to limitations in our measuring instruments, but rather a fundamental property of the quantum world. The uncertainty principle does not mean that the universe is inherently unpredictable or that our knowledge is limited. Instead, it tells us that there is an inherent fuzziness to the quantum world, a fundamental uncertainty that cannot be eliminated. Section 6. Quantum entanglement, spooky action at a distance. Perhaps the most bizarre and intriguing phenomenon in quantum physics is entanglement. When two particles become entangled, their fates become intertwined, no matter how far apart they are. Measuring the state of one particle instantaneously determines the state of the other particle, even if they are light years away. This spooky action at a distance, as Einstein famously called it, has puzzled physicists for decades. It seems to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. Despite its strangeness, entanglement has been experimentally verified numerous times. It has profound implications for our understanding of the nature of reality and the limitations of classical physics. Section 7. Quantum tunneling through the looking glass. Another mind-bending consequence of quantum mechanics is tunneling. In classical physics, an object cannot pass through a barrier if it does not have enough energy to overcome it. However, in the quantum world, particles can tunnel through barriers, even if they lack the necessary energy. Imagine a ball rolling up a hill. In classical physics, if the ball does not have enough energy to reach the top, it will roll back down. However, in the quantum world, there is a small probability that the ball will tunnel through the hill and appear on the other side. Quantum tunneling has important implications for various physical phenomena, such as nuclear fusion in stars and the operation of transistors in electronic devices. Section 8. Applications of quantum mechanics, from lasers to quantum computers. Quantum physics is not merely a theoretical curiosity. It has led to groundbreaking technological advancements that have transformed our world. From lasers and transistors to medical imaging and quantum computing, quantum mechanics is behind many of the technologies we rely on today. Lasers, for example, exploit the quantum property of stimulated emission to generate highly focused and coherent beams of light. Transistors, the building blocks of modern electronics, rely on the quantum behavior of electrons in semiconductors. Quantum computing, an emerging field with the potential to revolutionize various industries, harnesses the principles of superposition and entanglement to perform computations that are impossible for classical computers. Section 9. Conclusion. The unfolding quantum revolution. Quantum physics has unveiled a strange and counterintuitive realm, challenging our classical intuitions and revolutionizing our understanding of the universe. From the wave-particle duality of light to the uncertainty principle and entanglement, quantum mechanics has forced us to rethink our fundamental assumptions about reality. As we delve deeper into the quantum world, we continue to make groundbreaking discoveries that have profound implications for various fields, from medicine and materials science to energy and information technology. The quantum revolution is unfolding, and its impact on our world is only beginning to be felt.